I'm Hemnath from third year cybersecurity department. Now I'm going to explain about the A-star search algorithm. The A-star search algorithm, finding the optimal path, which discovers the elegant algorithm that revolutionized pathfinding and continues to power intelligent navigation systems across robotics, gaming, and artificial intelligence. Now we see the origin. The birth of A-star in robotics, a revolutionary breakthrough. In 1968, researchers Peter Hart Nils Nilsson and Bertrand Russell at Stanford Research Institute created A-stars to solve a fascinating challenge, enabling Shaky the robot to plan its own movements intelligently. Their innovation combined the exhaustive thoroughness of Dijkstra's algorithm with the speed of heuristic-driven greedy-based first search, creating a path-finding method that was both optimal and efficient. What is A-star? Graph traversal, weighted graphs, smart balancing. Graph traversal, a sophisticated algorithm that finds the shortest path between a start node and goal node by intelligently navigating through a weighted graph structure. Weighted graphs operates on graphs where nodes represent points of interest and edges represent paths with associated costs, allowing realistic modeling of real-world scenarios. Smart balancing balances actual cost travel so far, that is G, with estimated remaining cost to goal, that is H, to guide the search efficiently towards the optimal solution. The core formula of A-star search algorithm is f of n equal to g of n plus h of n, where g of n is the actual cost, which know the exact known cost from the start node to the current node, n representing the path already traveled. H of n, heuristic estimate, an educated guess of the cost from node n to the goal, must be unmissable, meaning it never overestimates the true remaining cost. F of n, total estimated cost, the complete estimated cost of cheapest solution passing through node n, guiding A star to always expand the most promising node next. How A star works step by step. Initialize the list, create two lists, open nodes awaiting exploration and closed nodes already evaluated. Begin with the start node in open. Select best node. From open, pick the node with lowest f of n value. This represents the most promising path forward. Generate successors. If the node is in the goal, generate all valid successor nodes. Calculate their G, H, and F values based on the correct path. Update and prune. Add promising successors to open wishlist, discarding worst duplicates. Move the current node to close to avoid revisiting. Reconstruct the path. When the goal node is reached, backtrack through parent node to reconstruct the optimal path from start to finish. Visualizing A star in the action. Dynamic exploration. Watch as A star intelligently expands nodes from the open list systematically, exploring the search space whilst avoiding dead ends and obstacles. Efficient discovery. The algorithm's heuristic guides it towards the goal, finding the shortest route far more efficiently than blind search methods. Real world applications and science. Robotics. Autonomous navigation systems use ASR to plan collision free paths around obstacles in dynamic environment. Video games. NPC pathfinding relies on A-star to create realistic, intelligent movement that responds naturally to terrain and obstacles. GPS and route planning. Navigation systems employ A-star to calculate the shortest or fastest routes on complex road networks with real-time traffic data. Logistics and AI. Supply chain optimization and AI decision-making systems leverage A-star for efficient route planning and resource allocation. Complete. Always finds a solution if one exists. Optimal. Guarantees the shortest path with admissible heuristics. Efficient. Minimizes unnecessary exploration with intelligent heuristics. Why A star remains essential? Perfect balance combines accuracy and completeness of Dijkstra's algorithm with the speed and efficiency of heuristic guided search methods. Guaranteed optimally. Mathematically proven to find the shortest path when using admissible and consistent heuristics. No guesswork, just results. Universal adaptability. Flexible enough to handle diverse domains and graph types from simple grids to complex weighted networks. A-star remains a smart choice for pathfinding problems, elegant in theory, powerful in practice, and essential for the future of intelligence systems. Now we'll go through one A-star search algorithm program. Here is the program. The first line is used for importing heap queue for the priority queue. A star needs to select the node with the lowest total cost efficiently. Then we define the weighted graph structure. Each node list is neighbors and edge weights. Define heuristic for each node. These are estimates of the cost to reach the goal node from any node. Open list. Open list initialization, a heap or priority queue ensures that the node with lowest F cost is processed next. Closed set. This tracks nodes already visited to prevent unnecessary revisits. Main loop continues until all possible paths are explored or the goal is reached. Pops from priority group. Always select and expand the most promising node. Goal check. If the node is the goal, the solution is found, return path and cost. Add node to visitor set. Prevent cycles and redundant computation. Neighbor iteration. Explore all the neighbor nodes, skip the visited neighbors, calculate the g cost and calculate the heuristic function. Now calculate the f cost by combining the total cost used for the priority. Push the neighbor to the queue, continue extending promising paths. No path case, returns failure. It's impossible to reach the goal. Function usage, demonstrate results for pathfinding for A to D. I will run this program. The total cost which I have found for the given heuristic function is 5 and the optimal path is ACD. Thank you.